go over the announcements. Well, first of all, your tests are graded, as are your previous labs. In general, you all did quite well on the test. The average was in the 90s. And so those grades are up on Blackboard, and you can pick up the graded tests and labs. The chapter 3 homeworks are due on Wednesday. Name?
Derek.
And so first chapter 3 homework is due on Wednesday. Second chapter 3 homework is due after spring break. And the quiz on chapter 3 is on Wednesday this week. If you need to take it early, come see me and we can work out when to take it early. And the chapter 4 homework will be due on the 18th of March. And we're starting chapter 4 because we're ahead of schedule. So let's get started on chapter 4 about work and energy. The work. Yes, you have a question? We have a lab today. Yes. Sorry, I didn't put that up, but yes, we have a lab. Work is the product of the magnitude of the force and the parallel distance through which the object moves. So if you apply a force over a distance, so the distance parallel to the force that the object moves through times the force gives you the work. I mean, strictly speaking, work is what's called the dot product of force and displacement. But work is force times distance. That's what you need to know for this class. And that distance is the distance in the direction of the force. So if you're applying a force in the direction that something is moving, you get positive work. If you're applying a force opposite the direction the thing is moving, you get negative force. Negative work, sorry. And mechanically, work involves both force and motion. So if nothing is moving, no work gets done. Then and if the motion is perpendicular to the force, also no work gets done. So here, no work is done because there's no movement. Distance is 0. Applying a force, but there's no movement, so the distance is 0. Here, something moves. So they're applying a force over a distance, so there's work done. And notice that the distance is the distance in the direction of the force. So here, our force is not in the same direction as our motion. There's 2 ways you can approach this. You can either talk about the distance in the direction of the force or the force in the direction of the motion. We'll use the force in the direction of the motion. So here, the horizontal component does work. The vertical component does no work. So you'll have a problem on your homework about this where they tell you, the size of the components, basically, and you need to figure out the work. I can write the more general formula for work. It actually works out to be that work is force times distance times the cosine of the angle between them. But you're not going to need to use that formula in this class. just remember this is, force times the parallel distance, or, the force in the direction of the distance times the distance. You can break it up either way. You can either do the distance in the direction of the force or the force in the direction of the distance. They end up working out to be the same. The units for work. Force times distance is a Newton meter, or a kilogram meter squared per second squared. And that is called a joule. The units, better one, units, 1 joule, which is 1 Newton meter, or 1 kilogram meter squared per second squared. And in the British system, it is a foot-pound, because it's a foot times a pound. And you may have noticed that these are the same units as torque. That is one of the weirdnesses of the universe. But yes, the units for torque and energy and work are the same. But they are different things. They just happen to have the same units. So often when you do work, you work against something. We feel the other part of Newton's third law of force acting against us. So if I am lifting this object up, I'm working against gravity. I am applying a force over a distance against gravity. So common things you work against when you're doing work are gravity, friction. So in the case of gravity, you have to apply a force to overcome the force of gravity. So weight is going to be work. The weight is mg, so the work is the weight times the height. So the work against gravity is mgh. So that's the work you do against gravity. It's the mass times, it's mg, the force of gravity, times the height. So if I lift this 1 kilogram mass, 1 meter, roughly, I have to do 1 kilogram times 9.8 meters per second squared times 1 meter. I have to do about 9.8 joules of work. So if I apply a 45 Newton force over a distance of 3 meters, how much work is done? Yes, and the units? So it's joules. Yeah. So it's force times distance, so newtons times meters, which is joules. And that's named after Joule, who did a bunch of early work on energy and stuff. So 45 newtons times 3 meters is 135 joules. Yes. So if a 45 Newton force does 90 joules of work, over what distance was the force applied? Yes. Because work equals force times distance. So distance equals work over force. 90 joules over 45 meters, 2 meters. I mean, 45 newtons is 2 meters. I am misspeaking today. Sorry about that. And here, if a force acting over a distance of 3.5 meters does 21 joules of work, what's the magnitude of the force? Okay. Yes. Work is force times distance. Force is work over distance. 21 joules over 3.5 meters is 6 newtons. Here, if a 3 kilogram mass falls a distance of 1.5 meters, how much work does gravity do? So this is not work done against gravity. This is the work done by gravity. But remember that the force of gravity, the weight, is going to be G times the mass. Yes, 44.1 joules. So work is force times distance. The force is the weight, which is mg. So the work is just going to be mgh. So 3 kilograms times 9.8 meters per second squared times 1.5 meters gives us 44.1 joules. That is also the work you would have to do to lift a 3 kilogram mass up 1.5 meters working against gravity. So if I drop it, gravity would do that much work. For me to lift it back up takes that much work. So energy is the ability to do work. Any object or system that possesses energy has the ability to do work. And when work is done by a system, the amount of energy in the system decreases. So if I do work, the amount of energy that I have decreases. And when work is done on a system, the system gains energy. So if I do work on something, that thing gains energy. So work is just the process by which energy is transferred from one object to another. And work and energy have the same units, and those units are joules. Because just work is energy in motion. So we're going to start by talking about the energy of motion. So this is kinetic energy. So kinetic energy is 1/2 mv squared. So this is the energy of an object that is moving. It is 1/2 times the mass times the velocity squared. And the direction of the velocity doesn't matter here. It's just the magnitude of it, because squaring it gets rid of the direction. So this is not a vector. This is just a number. So if an object is already moving, it has energy. And when you do work on an object, if you look at all the work that is done on an object, that will be its change in kinetic energy. So kinetic energy is 1/2 mv squared, and the work done on an object is change in kinetic energy. Kinetic energy 2 minus kinetic energy 1, or 1/2 mv2 squared minus 1/2 mv1 squared. So if you have a 1 kilogram ball is fired from a cannon, what is the change in the ball's kinetic energy when it accelerates from 4 meters per second to 8 meters per second? So here, we want to find change in kinetic energy, which is how much work is done on this ball while it's moving, while it's accelerating from 4 meters per second to 8 meters per second. The mass is 1 kilogram. V1 is 4 meters per second. V2 is 8 meters per second. So the change in kinetic energy is 1/2 times 1 kilogram times 8 meters per second squared minus 1/2 times 1 kilogram times 4 meters per second squared. So it's 32 joules minus 8 joules. So the change in kinetic energy is 24 joules. So in that period of time where it speeds up from 4 meters per second to 8 meters per second, it has 24 joules of work done. So you might also think about the work that is needed to stop a car. This is technically negative work, but it's still work. It's work against the car. So the work that's needed to stop a car is the braking force times the distance. And work is in that, there's a negative sign in there. But that is also that work is the change in kinetic energy for the car. So braking force times distance equals the kinetic energy of the car. That's how much energy has to be removed from the car. So 1/2 mass times velocity squared equals force times distance. And since force, mass, and 1/2 are all constants, distance ends up being proportional to your speed squared. So if you double your velocity, your braking distance increases by a factor of 4. You triple it, your braking distance increases by a factor of 9. That's why you have to leave so much more space while you're driving when you're driving faster. So the work required to stop a car is, the force of the brakes times the distance over which you brake. And the work you need to do to stop that car is the kinetic energy of the car, 1/2 mass of the car times the speed of the car squared. And so you can figure out that is proportional. So the distance required to come to a stop is proportional to the speed squared. So an 1,100 kilogram car travels at 36 kilometers per hour. What is its kinetic energy? Remember that 1 meter per second is equal to 3.6 kilometers per hour. So I'll let you work on this for a few minutes. No, you're off by a factor of 10. So kinetic energy is 1/2 mv squared. Our velocity is 10 meters per second. So 1/2 times 1,100 kilograms times 10 meters per second squared comes out to 55,000 joules. Here we have a 3 kilogram mass with kinetic energy of 13.5 joules. What's its velocity? So this is often a helpful thing to be able to do. If you solve this for velocity, you get velocity equals square root of 2 times kinetic energy over mass. So you divide by 1/2 mass and take the square root. So kinetic energy is 1/2 mv squared. So we can multiply by 2 and divide by mass to isolate v squared. So v squared equals 2 times kinetic energy over mass. So v is the square root of 2 times kinetic energy over mass. So 2 times 13.5 joules over 3 kilograms gives us 9 meters squared per second squared and a velocity of 3 meters per second. Here we have a bullet traveling at 300 meters per second. It has a kinetic energy of 900 joules. What is its mass? So here, kinetic energy is 1/2 mv squared. Mass is going to be twice kinetic energy over v squared over speed squared. So 2 times 900 over 300 meters per second squared, which comes out to 0.02 kilograms or 20 grams, which is a reasonable mass for a bullet. If anything, this bullet is a little light and a little slow. So here, this is a question about work. Remember, change in kinetic energy is equal to work. What force is necessary to bring a 900 kilogram car moving at 25 meters per second to a stop in 100 meters? So remember, work is force times distance. Change in kinetic energy equals work. There are some signs here, but the force does have to be opposite the direction of motion of the car, so the work it does is negative. But yeah. The work is equal to change in kinetic energy, so final kinetic energy minus initial. So 1/2 mv final squared minus 1/2 mv initial squared. The work is equal to 0 minus 1/2 mv initial squared. So the work here is going to be 1/2 times 900 kilograms times 25 meters per second squared, or minus 28,000, so 281,250 joules. But it's also force times distance. So the force is work over distance. The force is minus 281,250 joules over 100 meters. So the force required is minus 2,812.5 newtons, or minus 2,810 newtons. And it's negative because it's opposite the direction of motion of the car. That's why it comes out negative in this calculation. Because we basically assumed that the car is moving in the positive direction. Any questions about that? So, after falling 3 meters from rest, what's the kinetic energy of a 3 kilogram rock? So here, you need to figure out how much work is done on this rock as it falls 3 meters from rest. Because remember, work is equal to change in kinetic energy. It started at rest, so its initial kinetic energy is 0. Oh, oops. So work is change in kinetic energy, which is kinetic energy final minus kinetic energy initial. The initial kinetic energy is 0. So work is equal to kinetic energy final, and work is also equal to force times distance. Force times distance is going to be the weight, mg, times the height. That's kinetic energy final. So 3 kilograms times 9.8 meters per second squared times 3 meters gives you 88.2 joules. That is the kinetic energy of that 3 kilogram rock that has fallen a distance of 3 meters. Its velocity, well, kinetic energy is 1/2 mv squared. So v squared is 2 times kinetic energy over mass. So the square root of 2 times kinetic energy over mass gives you velocity. So square root of 2 times 88.2 joules over 3 kilograms. Square root of 58.8 meters squared per second squared, or 7.67 meters per second. Meters per second. We are ahead of it. I will introduce potential energy and then we'll start the lab early because we're ahead of schedule. So potential energy is the energy an object has because of its position or location. It is the energy of position. Basically, certain forces are what are called conservative, and conservative forces are forces where basically the work you do against the force, you can get back afterwards. So like for gravity, I can do work against gravity, and then I can drop this and get that work back as kinetic energy. So most potential energy we're going to talk about is due to gravity. Basically, we can store energy in position by raising things up. So work is force times distance. Weight is mg. So if we substitute in height for d, the work is mgh. Gravitational potential energy is mgh. That's the only sort of potential energy we're going to talk about, really. There are other types of potential energy. You can store potential energy in springs. There's electrical potential energy. There are various others as well. So gravitational potential energy is equal to the work done, and this is equal to the weight times the height. So the amount of work you need to do to lift a 1 kilogram book to the height of 1 meter is 1 kilogram times 9.8 meters per second squared times 1 meter, which is 9.8 joules. And once you've lifted that 1 kilogram book up, you could extract that energy or get that energy back by letting it fall. So the other nice thing about potential energy is it depends only on the initial and final positions. It doesn't matter what path you take. It is independent of path. So if you disregard any frictional loss, it takes the same amount of work to lift this mass, no matter what path we take. So it might be easier to push a mass up a ramp, but it's easier to push a mass up a ramp because you get to use a smaller force over a longer distance. So you're doing the same amount of work, but you're doing it in a less concentrated manner, so you don't have to generate as much force. So you can also think about work being change in potential energy. So work is done when there is a change in position, and therefore the reference point for measuring heights is arbitrary, but you need to be consistent about it throughout your problems. You need to be internally consistent. So you could do your entire problem measuring from the height of the table or from the height of the ground outside, whichever is more convenient. But you can't measure one measurement from the table and the other from the ground outside. You need to use the same reference for everything. So no matter which scale, delta H is the same. So here's two different scales, one where H is 0 is in the middle, one where 0 is on the bottom, but the change in height from -50 to 50 and from 0 to 100 is the same. It is 100. Some other things that contain potential energy are strings, compressed or stretched springs, a bowstring, though actually, in truth, a bow does not contain most of its potential energy in the string. It's mostly in the bending of the limbs. So it's also a spring. And then there's like electrical potential energy and other things. And I think that's where I'm going to stop for today. We'll go over this again on Wednesday. But we can now do the lab.